So we begin with deadlocks chapter, so which is there in your module 3. Okay. So here in this lecture we are going to learn about deadlock problem. Okay. So what do you mean by a deadlock? Then system model. So how in the operating system, so we are going to handle the deadlock, or how the system is going to use a resource, how is allocated, how it is released, all that. Okay. And then we are dealing with the deadlock characteristics, methods for handling a deadlock. So then we are going to learn how deadlock can be prevented, so deadlock avoidance, deadlock reduction, and recovery from deadlock. Okay. So next next slide. Okay. So the objective is first to know what is the meaning of a deadlock. Okay. So we should describe what do you mean by deadlock. Okay. And to present the number of different methods for preventing or avoiding a deadlock in a computer system. Okay. So this is the objective of this particular chapter. Okay. So first let us know what do you mean by a deadlock. Okay. So when we have a deadlock, okay, so whenever some set of processes are there in the system, okay, and after executing for some time, so the system itself gets hanged up. Okay. So this situation we are calling it as a deadlock. Okay. A set of block process will be there, okay, each holding some resources, and it is waiting to acquire a resource which may be held up by some other process. Okay. So example, say if you are having two tape drives. Okay. So P0 and P1 is holding one tape drive, okay, and each needs another one. So that means P0 process P0 is having one tape drive, and it needs one more. So that means to execute completely, P0 needs two tape drives. Okay. And it's the same case with P1. So P1 to execute completely, it needs two tape drives. Okay. But currently it is holding one. Okay. Now P0 is holding one tape drive, and P1 is holding another tape drive. Okay. Now both of them are not ready to leave their tape drives. Okay. So now P0 can't complete its execution until it gets one more tape drive. Okay. Similar is the case with the P1. So it can't complete the execution when it until unless it gets another tape drive. Okay. So situation will be like that. So both are holding one tape drive and waiting for one more which is held up by the other process. Okay. So now the situation will be no one will be executing. So this is a deadlock situation. Okay. Another example we can see using a semaphores, what we have seen in the process synchronization. Okay. So semaphores normally will be operating with the two operations, wait and signal operation. Okay. So here we have two semaphore variable. One is variable A, semaphore variable A, and semaphore variable B. Okay, initialized to 1. Okay. Now you can see that whichever process executes a wait on one particular semaphore variable first, okay, so that is not going to wait in a busy loop. Okay. So that is going to decrement. Wait operation is normally decrementing the value if it is 1. Okay. If it is already 0, it is not going to decrement, it just busy wait in that particular loop. Okay. So in the process P0, A value initially will be 1, so it is 1, so it decrements, okay, and makes it to 0. After decrementing, okay, the value is 0, but it enters the next statement. Okay. Similarly here wait B initialized to 1, so once it is seeing it to be 1, okay, so it will be busy waiting if the value of B was 0. Now it is 1, it is decrementing and then entering at this state. Okay. Now here the value of B was made to be 0 by P1. Here the value of A was made to be 0 by this one. Okay. Now in the semaphore we have seen that if the value of a semaphore variable is 0, okay, it is busy waiting there itself. Okay. It is not going to next statement. Okay. So now here, because the way how your wait operation is used in P0 and P1, okay, the process will not further execute. Okay. So neither P0 will execute, neither P1 will execute. So this situation we are calling it to be a deadlock situation. Okay. So deadlock situation says that no process will be executing, it is holding some of our resources but waiting for the other process to execute. So this is a simple example. Okay. We are having a bridge. Okay. So this bridge is having, okay, space, okay, so where only one car can move. Okay. Now here you can see that one car has come from this direction, other car has come from the opposite direction. Okay. Now there is a space for only one car to move. Okay. When these two cars are facing each other, okay, if either one of them is going to leave the space, it is moving back and leaving a space, then there will be no blockage. Okay. So if no one are ready to go back, so what will happen? Eventually all the vehicles will start blocking it here and also blocking it here. Okay, so the situation will be no cars will be able to move in. Okay, so this situation we can call it as a deadlock. Okay, so this situation this kind of situation can also be seen in the system when there are some process which are executing and not able to get the resources. Okay, so now system model. So the system model here says that how the operating system is going to deal, okay, how it is going to use the resources. Okay, so how it has been followed in the operating system. Okay, so you have naming the resource type with the resource R1 to Rm. Okay, now that means whatever number of resources you're going to have, each resource you're going to label. Okay, so that means R1, R2, R3, so on till Rm. Okay, the resources can be either your CPU. Okay, so when I talk about CPU, you can call it as a CPU cycles. Okay, so CPU cycles means whichever process executing in CPU, you can say that it is using the CPU cycles. Okay, your memory space can also be a resource. Okay, your IO device can also be a resource. Any IO device can also be a resource. So each will be designated by a particular R. Suppose if you are having a IO device, any input device. Okay, so like joystick. Okay, so it may be named as, okay, R2 or for whatever it is. Okay, so you have a set of resources, each is labeled by resource R1, R2 and so on. Okay, each resource type Ri has Wi instances. So that means if I am going to label a resources, okay, so R1 to Rn, so in that any particular resource can have a Wi instance. So like if I am having a resource tape drives, okay, if I am having a resource CPU, if I am having a resource disk, okay, and I am having a resource files. So there are 4 resources. Okay, so tape drive, disk, okay, file and CPU. Okay, so now in that, okay, if I am labeling, okay, tape drive as R1. Okay, now if I am having 3 tape drives in my system, so that I am calling, okay, and that there are 3 instances of resource type R1. Okay, so like that, okay, if I am having more number of disks, okay, so let me say that I have labeled disk, okay, with the name R2. Okay, now I can say that, okay, resource type R2 is having 2 instances, that means I am having 2 disks. Okay, so this is how we are going to follow the naming convention. Okay, now each process utilize a resource as follows. Okay, so first any process, okay, will make a request for a resource. Okay, and then once a request can be accepted immediately or can be blocked for some time by the operating system depending on the availability of your resources. Okay, and after the resource is allocated to the process by the operating system, the process is going to use that particular resource. Okay, so after the usage, the process is going to release the resources. Okay, so at any moment of time, the operating system will have a tables in which it is having a information that how many resources are being allocated to which the other process. Okay, so which are free available resources. Okay, it will have a list of free available resources. It will have a list of the allocated resources and even to which process it is allocated. All the details is there with the operating system. Okay, so this is a system model how, okay, resources and the process are utilizing. Okay, now let's learn about the characteristics of your deadlock. Okay, a deadlock can arise if 4 conditions hold simultaneously. Okay, so a deadlock can arise if 4 conditions hold simultaneously. So those 4 conditions are mutual exclusion, hold and wait, no preemption, circular wait. Okay, so mutual exclusion, only one process at a time can use a resource. Okay, so if I am going to use a resource, okay, the other one can't use that resource. Okay, so only one process at a time can use a resource. Okay, so let's say like example, the best example is a printer. Okay, so if I am using a printer, no other student, okay, in the lab is using that particular printer. Okay, if one particular student, okay, so is using a particular resource, okay, and then the other students can't use a printer at the same moment of time. So this condition we are calling it as a mutual exclusion. Okay, and then hold and wait. Okay, so hold and wait. So that means a process is holding some resource and waiting for additional resources to acquire, okay, which is held up by some other process. So this is called as a hold and wait. You are holding something and waiting for something. Okay, a process holding at least one resource, okay, and it is waiting to acquire the additional resources held up by some other process. Okay, so this situation is called as a hold and wait. Okay, next characteristics is no preemption. A resource can be released only voluntarily by the process holding it, okay, after that process has completed its task. Okay, so that means once the resource is allocated to a process, okay, you cannot remove that resource from that particular process. Okay, so the process has to voluntarily release that resource. Okay, otherwise you cannot force the process to release that particular resource. So releasing means after the usage it's going to leave off. Okay, so that's called as a releasing of a resource. Okay, no preemption means once you are giving a resource to any particular process, okay, it voluntarily has to give it. Okay, you cannot force that process to leave that particular resource. So this is called as a no preemption of a resource. Okay, and then circular wait. Okay, so the circular wait says that there exists a set of process P0, P1, okay, so to Pn. Okay, let's say you have 5 process P0, P1, P2, P3, P4. Okay, now P0 is waiting for a resource that is held up by that process P0 is waiting for a resource that is held up by P1. Okay, so P1 is waiting for a resource that is held up by P2. Okay, and P2 is waiting for a resource that is held up by P3. Okay, and P3 is waiting for a resource that is held up by P4. Okay, and P4 is waiting for a resource that is held up by P0 again. Okay, you have come back again. So that means this is a circular waiting. One is waiting for other in a circular fashion. So this is called as a circular wait. Okay, so if all these conditions, 4 conditions hold together, okay, then we can say that deadlock will occur. Okay, for a deadlock to arise, all these 4 conditions has to hold simultaneously. Only then we can say that deadlock can arise. Okay, so if you say only one condition is there and the condition is absent, okay, so you cannot say deadlock may not arise. Okay, so deadlock will arise only when all these 4 conditions are holding together. Okay, next, resource allocation graph. Okay, so resource allocation graph will tell us whether there is a deadlock in the system or not. Okay, so you have a resource allocation graph, a set of vertices V, okay, and a set of edges E. Okay, now in a set of vertices we are having 2 sets. One set you designate as P, okay, another set you designate as R. Okay, the set P defines the number of processes are there which are there in the system. Okay, the set R defines the number of resources types available in the system. So it was not defining the number of resources, it was defining the number of resources types. So that means how many different types of resources are there in the system. Okay, now number of resources is we speak about an instance of resource. Okay, so here it is defining the total number of types of resources available. Okay, now next thing is edge. Okay, so now resource allocation graph consists of set of vertices and set of edges. Okay, so edge, now in the edges we have 2 types of edge. One is called as a request edge and another is called as a assignment edge. Okay, so request edge is a directed edge from a process P1 to Rj. Okay, so process P1 is requesting for resource Rj. Okay, so it is not yet been assigned, but it is requesting for a resource Rj. Okay, so assignment edge is a directed edge. Okay, the process Rj is assigned to process P1. So that means the process Rj is already been allocated by the operating system to process Pj. Okay, so this is called as a assignment edge. So request edge is written in this fashion, assignment edge is written in this fashion. Okay, now we have known what is vertices and edges, what is your request edge and what is your assignment edge. Okay, now let us see what are the notations, okay, which we give it to the process and the resource. Okay, so process is always denoted by a circle, okay, and resource type with 4 instances. The resource type is indicated by a square. Okay, and the number of instances of that resource is indicated by small dots in the square. Okay, now Pi is requesting instance of resource Rj. Okay, so we are pointing Pi requesting instance of resource Rj. So likewise, so this is a request edge, okay, which is shown in the graph. Okay, so Pi is holding an instance of Rj. Okay, now here it is requesting, it is not the any of your instance of Rj is not allocated to Pi. Okay. Now in this case, Rj, one instance of Rj is allocated to Pi. Okay. Now see here is a resource allocation graph. Okay. Now you can see that, okay, process Pi is requesting for resource type R1. Okay. So process P1 is requesting for resource R1. So R1 is assigned to process P2. So P2 is requesting for R3. Okay, and this is assigned to P3. Okay, and now here R2 is, there are two instances of type R2. Okay, R2 is assigned to P1 and one more instance of R2 is assigned to P2. Okay, so you have, okay, resource R4 which is having 3 instances. Okay, right now it has not been allocated to any other process. So this is called as a resource allocation graph. Okay, now here we don't have any cycles. When we don't have any cycles in the resource allocation graph, so there is no deadlock in the system. Okay, so will there be a deadlock here? Okay, now here P1 is requesting for R1. Okay, R1 is assigned to P2. Okay, which is requesting for R3, and R3 is assigned to P3. So P3 is requesting for R2. Okay, and R2 is assigned to P1. So this is one cycle, you can define it here. Okay, so like that, if you are taking in this fashion, you are having one more cycle. Okay, so when you have a cycle in a graph, okay, so now here a deadlock exists. Deadlock may occur. Okay, we cannot definitely say that deadlock will occur. If there is a cycle in a graph, okay, then there are chances that deadlock has occurred. Okay, so if there is cycle, in some cases cycle will be there but there will be no deadlock. Okay, now here P1 is requesting for R1, R1 is assigned to P3, so P3 is requesting for R2, R2 is assigned to P1. Here also there is a cycle. Okay, now here there is a process P1, okay, P2 here. So after executing, okay, this is going to release this resource. Okay, so by which you can break the cycle. So here in this case, though there is a cycle, there is no deadlock. Okay, so now by this we can make a conclusion that if a graph contains no cycle, no deadlock. If a graph contains a cycle, okay, in that you have to follow with two scenarios. Okay, so if only one instance per resource type, then deadlock is there. Okay, if several instances per resource type, possibility of deadlock may be there. Deadlock may be there, may not be there. Okay, so now what are the different methods for handling the deadlock? Okay, so the different methods of handling a deadlock is, first thing, prevention is better than cure. So that means we are ensuring that system will never enter a deadlock state. Okay, now here there are two methods what we go for. Okay, now deadlock prevention and deadlock avoidance. So this will come into this particular measure. Okay, and next method is allow the system to enter a deadlock state and then recover from it. Okay, that's the second one. So that means you detect a deadlock and then recover from it. Okay, and the third one is, it's very simple, ignore a problem. Okay, you ignore the problem and pretend that deadlock never occurs in the system. So this thing also is used by most of the operating system, including the Unix. Okay, this methods. Okay, so first measure is deadlock prevention, deadlock avoidance. Okay, so that comes in the first method, and second one, deadlock reduction. So these are the standard methods, so using which you have taken measures to handle the deadlock. Okay, now deadlock prevention. Okay, so deadlock prevention says that, okay, so you know that there are 4 necessary conditions for a deadlock to occur. Okay, mutual exclusion, hold and wait, no preemption, and circular wait. Okay, if you break any of these 4 conditions, any one of these 4 conditions, okay, you can prevent a deadlock from occurring. Okay, so that's how you're going to prevent a deadlock from occurring. Okay, you know that all the 4 conditions simultaneously should hold, only then the deadlock can arise. Okay, so now if you are preparing a system, okay, if you are preparing some of a protocol in such a way that these conditions will never hold, okay, or one of the conditions may not hold, then deadlock will not occur. Okay, now let us see one by one how we are going to deal with each of the case. So mutual exclusion. So okay, mutual exclusion means not required for shareable resource. Okay, at a time only one process can use a resource. Okay, so that is called as a mutual exclusion. Okay, if I am using, you cannot use. If you are using, I cannot use. Okay, that is called as a mutual exclusion. Now this is not at all required for shareable resource. Okay, so because everybody are using it, okay, at a time we are going to use a resource, okay, a shareable resource. Okay, so this is not concerned to your shareable resource. Okay, but you cannot avoid this for non-shareable resource. Okay, I cannot tell that a printer can be shared by more than one person at the same time. Only one user has to use it, or only one process has to use it. Okay, so this you cannot avoid whenever you are dealing with a non-shareable resource. Okay, then hold and wait. Okay, hold and wait must guarantee that whenever a process requests a resource, okay, it does not hold any other resource. Okay, so hold and wait, holding some, waiting for some other thing. Okay, so now you have to guarantee that whenever a process requesting a resource, it does not hold any other resource. Okay, so there are two protocols what we can follow. Okay, so require process to request, okay, and be allocated required, okay, or required resources whatever process wants be allocated before it starts execution. So that means whenever a process starts execution, before the beginning only you are allocating all the resources to that. Okay, so that is one method. Okay, at the starting itself, whatever resources it has needs, so it is claiming it, so you give all the resources to it. Okay, so that means here what we are avoiding, we are avoiding a wait. Okay, holding something, waiting for something. Okay, so here what we are doing, so everything whatever it needs you allocate. Okay, and it is not waiting for any resource, so it has been allocated to all the resources whatever it wants, and it will use all of them, execute it and leave it off, and so that released resources can be again utilized by some other process. That is one method. Okay, other method, okay, allow process to request resource only when the process is none. Okay, so that means some resources it has holding it. Okay, now before, if it need arise to request few more resources. Okay, so now thinking in mind that whatever resources it has already been holding it, now the work of that resource is over. Now let it release that resource and it can request a new resource. Okay, so here also what we are doing, so if it is requesting for a new resource, okay, now it has to release all the resources whatever it is going to have. Okay, so this is how you can avoid a holding. Okay, or if you are not able to allocate any resource, you leave all the resources. Okay, now in this protocol we are having low resource utilization, okay, and starvation problem. Okay, so low resource utilization means, so initially itself we allocate all the resources to a process, so most of the time, okay, the resources may be idle without usage. Okay, so that because, okay, initially it has claimed all of them. Okay, it may need that resource in the middle and it may need that resource at the end. Okay, so but it has claimed and it has been allocated all of them, so this is called as a low resource utilization. So it leads also to starvation problem. Okay, some process will never get a particular resource because at least some process may have claimed it and be allocated, so this also leads to a starvation problem. Okay, but if you follow that, okay, there is some method, some scope that, okay, you can prevent a deadlock. Then no preemption. So no preemption says that you cannot preempt any of a resource. Okay, if a process that is holding some resource request another resource that cannot be immediately allocated to it, then all the resources currently being held are to be released off. Okay, no preemption of resource. That means a process cannot release a resource. Okay, it has to do it voluntarily. But here, if it is requesting for, you design a protocol in such a way that if it is requesting for some resource, immediately the request can't be sanctioned, then whatever it is having, leave it off. Okay, let it release, so that those resources can be utilized by the other process. Okay, so preempted resources are added to the list of resources for which the process is waiting. So process will be restarted when it can regain its old resources as well as a new resources you're going, whatever it is going to request. Okay, and then circular wait. Okay, now circular wait, we have to break a chain. Okay, now you impose a total ordering of resource type and require that each process requires resources, okay, in an increasing order of your enumeration. So that means we are going to assign some numbers, okay, to each process in that particular order only they have to request, okay, so that there will be no circular wait. Okay, so that we are calling it as a enumeration. Okay, and then deadlock avoidance. Okay, so this is similar to your prevention, but some additional information you are going to add it. Okay, and then there are certain algorithms. Okay, so what we are calling it as a deadlock avoidance algorithm. Okay, so that is deadlock prevention avoidance will come into your first measure. Okay, so requires that, so you require some prior information. Okay, so you need to know what are the maximum resources a process may use. So this is a advanced information a process has to give it to the operating system. Okay, so if you know that, then you can avoid a deadlock. Okay, so the examines the resource allocation state, okay, to ensure that there cannot be a circular wait condition. Okay, now here you are going to allocate, okay, resource allocation state, because it is the OS is knowing what all the resources are required by each process. That is information is given in advance. By seeing this, it will see the allocation state, okay, and it will see that there is no circular wait in that. Okay, so resource allocation state is defined by number of your available and allocated resources. Okay, you are saying how many are freely available and how many are allocated resources, and the maximum demand of the process. Okay, so deadlock detection. So the third second measure is deadlock detection. Allows system to enter the deadlock state, okay, and detect the you have certain detection algorithm which will detect a deadlock. Okay, after you detect a deadlock, and then you have run some certain algorithm from where you can recover the deadlock. Okay, so now we need to learn about the safe sequence. Okay, before going to learn about what is the deadlock avoidance algorithm, okay, how that algorithm works. So for that we need to know one particular term called as a safe state. Okay, so we say that a process requests available resource. Okay, so now system must decide if immediate allocation leave the system in a safe state. So this means that whenever a process requests a resource, the OS, the operating system, has to think that if it allocates a resource to this, or if it grants a request, or if it sanctions a resource request by a process, okay, then in future whether this allocation is going to lead to a problem. Okay, so that also has to be thought by the operating system. Okay, so for that you will find a safe sequence. So system is a safe sequence if there exists a safe state, if there exists a safe sequence of all the process. Okay, now here what actually the OS will do is it will actually pretend acting like it has allocated resources and then find out a safe sequence. Okay, so by allocating it, pretend to allocate, modify the data structure tentatively and find the safe sequence. If it is finding a safe sequence, then the system will be in a safe state. Okay, so if it is finding a safe sequence, then actually the request will be sanctioned. Okay, so sequence P1 P2 to Pn is safe sequence if each process, if for each Pi, okay, the resource that Pi can still request can be satisfied by the currently available resources plus resources held up by Pj, where j is less than I. So that means here if you are having P1 to P1, P2, P3, P4 to Pn, okay, so the request of P2, okay, which can be satisfied by the resources currently held up by P2, and the resources which can be released after execution by P1. Okay, so likewise if you are having P3, okay, so the request of, if your P3 is requesting, so it can be satisfied by the resources currently held up by P3 and the requested resources by P2. Okay, so where j is less than I, so here 2 is less than 3. Okay, so here you find such a safe sequence. Okay, so you pretend as allocating, and if you end up in finding a safe sequence, then you will be entering a safe state. Okay, if Pi resource needs a not immediately available, then Pi can wait until all Pj have finished. Okay, so that means if P2 is requesting for something, if it is not getting a resource at that instant of time, so it is waiting for P1 to finish. Okay, like that, if you are having P4, so P4 is requesting for something, not able to get that resource at the same instant of time, so it has to wait for all the J's to finish. That means it has to wait for the process P1, P2 and P3 to finish. Okay, when Pi is finished, okay, Pj is finished, Pi can obtain needed resources, okay, execute, return the allocated resource. That means suppose if P4 is there whose request is not allocated, okay, it is to wait till P1, P2 and P3 finish. So when these process finish, okay, they are going to release all the resources whatever it is going to have, okay, and they will be added to the list of your free resources. Okay, when Pi terminates, Pi plus 1 can obtain its needed resources and so on. So suppose if P1 terminates, so P2 can use the resources from P1. Okay, so this is how it's going to work out. Okay, now like this, if you are getting a safe state, okay, if the system is in safe state, okay, then there is no deadlock. If a system is in unsafe state, the possibility of a deadlock may occur. Okay, so avoidance ensures that the system will never enter a unsafe state. Okay, so if you have a safe sequence, no deadlock. Okay, unsafe state, so deadlock may occur. Okay, so now you have resource allocation graph. Earlier we have learned. Now here we are having a resource allocation graph algorithm. Okay, now in addition to your request edge and assignment edge, we also have a new edge. Okay, so that we are calling it as a claim edge. So claim edge, actually you have a dotted line, okay, with arrow mark. Okay, so Pi, you are having a claim edge to Rj. That means in future, okay, so process Pi can claim for resource edge. Okay, so claim edge converts to request edge when a process requests a resource. When a resource is read by a process, okay, assignment edge reconverts to a claim edge. So this is to say that resource is already allocated to process. So after using it, again it releases. Okay, again you reconvert that particular assignment edge to claim edge, thinking that in future again the request may come for the same resource. Okay, so now here resource the condition, okay, here to find out deadlock is, okay, now you need to have prior information. Okay, so that means the resources should be claimed further. Okay, I mean initially itself we have given the resources. Okay, so resource allocation graph for deadlock avoidance. Okay, now here R1 is allocated to P1. Okay, so P2 is requesting for R1. Okay, so you are having, okay, P2 requesting, I mean P2 claiming for R2 and P1 is also claiming for R2. Okay, so here you may have a deadlock in a future. Okay, so whenever request is sanctioned, you need to be very careful. Okay, so that you don't go into a unsafe state. Okay, so here in the previous case, okay, P2 has a claim edge from, okay, P2 to R2. So in this case, in this example, okay, R2 has changed to P2. That means, okay, so your claim edge has turned into request edge was assigned, so this has changed to your P2. Okay. Now examples of your avoidance algorithm are, okay, banker's algorithm, resource request algorithm and safety algorithm. Actually all the algorithms are important. Okay, among that normally your banker's algorithm will be repeatedly asked in the examination. So from the exam perspective, so banker's algorithm you need to study, you give importance for that, but resource request algorithm and safety algorithm are also equally important.